robotics and intelligent machines. So where we, when we talk about artificial intelligence applied to the machines and robotics in general, no? Which is actually, it's this kind of machine intelligence is part of my second. Today I will divide the day in two parts mainly. The second part will deal with this robotics intelligence that might interest Professor Khanna, that is on artificial intelligence, and all the people that are working more on data than other things. Okay, tell me when you want that I start.
Yeah, we will have a small session in.
We missed.
Yeah, I think there was some problem with the madam's connection. Seems to be some. So,
Sorry, I got disconnected, in fact, yeah. Yeah, please continue, Professor.
yeah, madam, you can continue actually if we haven't started yet.
Okay. Okay. So, very warm welcome to all of you who are present today, especially my colleagues and students and participants from across India. It's a matter of pleasure for all of us that today we are starting the course, GIAN course on human-centered robotics. You know that this is one of the most important areas of research and development in recent years, because robotics has not only been limited to manufacturing or very critical applications, but it has also entered the domains where lives of people are important, or it is assisting people for a better life. So we are so glad that Professor Domenico Pretichizzo accepted our invitation 3 years back when we were planning this course. And he very kindly agreed to deliver a course of lectures on human-centered robotics. In fact, it was his idea that we should keep the topic on human-centered robotics. Professor Domenico Pretichizzo is a full professor of robotics and automation at the University of Siena and a senior scientist at Italian Institute of Technology in Genova. He is also the co-founder of Weird, a startup on wearable haptics and tactile communications. Professor is basically an internationally renowned expert in the field of haptics, robotics, and wearable technology. Main applications of his research works are in virtual and augmented reality scenarios and in the rehabilitation of people with upper and lower limbs disability, visual and cognitive impairments. He has been awarded the fellowship of Institute of Electrical and Electronics Engineers in 2016 for his outstanding contribution to haptics and multi-fingered robotics hands. So participants, we are very fortunate that he has given consent, and today he is present with us. I request Professor Gupta to say a few words before we formally begin the keynote by Professor Domenico. Thank you.
Thank you, Madam. And we welcome Professor Domenico for giving this series of the lectures, basically. Next 4 days, he will be delivering number of lectures related to human-centric robotics. So thank you very much, Professor Domenico, for accepting our invitation and delivering this. Thank you.
Great. So let me say a few words. Sorry, can I start?
Just one more welcome to you, because after all these years, we have been so keen to listen to you. I request Dr. Mukesh Roy, who is the whole soul in charge for making it happen. I request Dr. Mukesh Roy to welcome you on behalf of the Institute. Thank you.
Yeah, definitely. And of course, Professor Domenico, it's indeed, as I told you, it's a pleasure. And not only that, it's an honor for us to have there you as a faculty in charge for this course from the outside. And let me tell you, in this connected world, of course, during the Corona, I have learned a lot. And just because of the Corona, via online mode, we learned a lot how to use the knowledge of the other people, and just utilizing those knowledge, we are trying to learn more and more from you, sir. And definitely, as I told, all the students will be benefited here, whoever are participating in this one. It's not only the student, like faculty members are also there. And we are running not many, basically GIAN courses, and even in future also, I would like to have different coordination with you, sir. So thank you just to be here, sir. And indeed, again, pleasure, sir. Thank you.
Thank you, Dr. Roy. Thank you. So we now invite Professor Domenico Pretichizzo for delivering his keynote on wearable robotics for better life. Thank you so much for accepting our invitation. Thank you.
Thank you to all of you for this kind introduction. And I am really thankful to all of you, Professor Ogia and the whole group that started collaborating with me to have this initiative, and then the coordinator of the GIAN initiative, Professor Kumar Roy, and all the ones that said words on my talk here. So it's for me a pleasure and an honor for me to be part of this great initiative that is GIAN. So my talk is not only a talk, keynote is not only a keynote, want to be a sort of presentation of possible initiative that we are working on, that possibly we can find collaboration together in this global world. You know why? Because I think that now, I don't know what is your feeling. I think that here there are both professors and scientists, and the student here attending. But I mean, I'm talking to you professors that are working in your institution in research. So sometimes, so I'm leading a huge group, a group of almost 20 people working across Siena and Genova and the places of where the startup are, no? And I don't know what is your feeling, but now I think that most of the research that before was done mainly and exclusively in academia research, now there are huge company, huge multinationals like I don't know, Amazon Robotics, whatever you think about a big company like who is going on Mars, So on Mars is going probably a private company, not a university, not a research group. So this means that, in my opinion, the research is changing, no? Is changing a lot and is moving towards not only university. This means that in some sense, in order to get the right, to obtain the right energy from us, we need to change a little bit. We cannot stay alone anymore. So even if I have a huge group, no, like a 20, 30 postdoc, PhD, whatever, collaboration, but I think that the model of the research that we need to invent as professor, again, should be a little bit different. It cannot stay in a lab, in a university, even the most prestigious one, cannot stay there. Think about the vaccine. The vaccine has not been invented by a university, has been invented by a company that is Pfizer, no? That is one of the companies that invented the vaccine. What I want to say is that in order to be competitive now in very advanced research, we need to break the walls of our labs and try to integrate our competence in a sort of global academic system that involves not only my lab, not only Italy, not only Europe, but goes across universities. So I think that we really need to change the way we were doing research, because now our big competitors at the global level are not other academic colleagues, but are multinational. So only if we change our mindset and we go towards a more systematic view of doing research, we can probably make something that makes a big difference in research, especially, but not only when we talk about technology, of course. So I think that this should be a sort of initial step of a larger collaboration to think about new models of doing research, which means collaborating, getting funds, and writing papers, making experiments, doing prototypes, whatever. Okay. So what I want to do with this talk is with this keynote, is to inspire not your brains, our brains, including mine, to find a common ground where we can establish future collaboration that, of course, will start exchanging students, exchanging professors, but mainly means to enlarge our labs and having a sort of a meta laboratory across countries in order to be competitive with these huge multinational research centers that are pushing our boundary very, deeply across the research. I mean, I don't know if you agree. We can open a discussion later on this, but now let me start with my talk. So I will share the screen. I like to be interrupted, so in case, I will ask you questions and probably, I will try to be as interactive as possible, because as the coordinator of GIAN said, this possibility of collaborating online is probably the infrastructure to create something bigger that I was talking about before. I think that you can see my screen.
Yes, we can see, and very nice forward, I would say. We really appreciate that, and definitely beyond any boundaries, if you think about that, that's great. Yes, we can see that. It was full screen, and then
no, I'm just hiding the floating control. Okay.
Great, yeah.
So this is the title of my talk, and I will also try to, while I'm talking about the subjects of my research, and I will also try to give you idea on how my lab has been growing over the years. So not only the things that we were doing, but also the way we were doing it. And of course, the way of running a research lab is something that goes, is really interdisciplinary, no? Because goes, you know, is for robotics, is for aeronautics, whatever is the lab, the way we run our labs, our scientific group is common to all of the scientists that are here. And even the students that will do research in the future, either in companies or in a university or government, managing the research will be something that is really important to understand. Okay, well, this is my lab. Actually, this is also something that I want to show you. There are the two main buildings. One, the top one is the one in Siena. Siena is in the center of Italy. Actually is in the middle between Florence and Rome. Is a very ancient medieval city. It's a very interesting place to live in. The building at the bottom is the Italian Institute of Technology. That is an Italian initiative from the government, where all that they do, we do actually research in robotics, nanotechnology, and health in general. And I have been, I have a second appointment with them since 2009. So my lab is across Genova and Siena. And also I have two startups in Milano, and then I will talk about the startup as well. Well, these are some shots of my lab, and I want to present this shot of my lab because I want to tell you that there is you know, there is something in common to all these images, no? What is in common are the hands, okay? So you can see hand manipulating an object, hand doing a teleoperation, hands in virtual reality. You know, hand is a common element of all this picture. Why? Because I decided in my life to be really vertical, in the sense that we really focused on something, I would say, super specific in the research panorama. Because we wanted to be, you know, because I think that right now in this global world, if you are really focused on something, then you can establish your signature in research. So you in general will be recognized if you do something very specific. In some sense, we have been you know, obsessed over the years about the things that we do, and this is the way we sell our research. This is the way we tell the story of our research. So we are focused on mainly on hands, okay? But hands is a general concept. Hands is not. I want to have probably a better. Not sure if I can. Let me see if I can. I want to. No, not easy, but it's not a problem at all. I will do it in the pause. Okay, I want you to see even my hands. Can you see me, right? Okay, so the hands,
yes,
the hands.
Yes, we can see.
The hand is, you know, the hand is a big concept. So the hand means basically manipulating objects, okay? But manipulating objects like this, no? It's not only the hand. So the mathematics that we do is also, so this also can be seen as 3 robots like index, a middle finger, and a thumb that collaborate with the same objects. Now, so with the manipulation, with the hand manipulation, you have in your brain also all the mathematics of the multiple robot collaboration. So if you have to, if you have many robots that work on the same car model, then it's exactly the same strategies of having multiple manipulation. Hands is not only robotic hands, but it's also human hands. Okay, so robotic hands, of course, is the end effector of a robot. A robotic arm as an end effector that is a hand, and it's very important because if you don't have the end effector, you cannot do anything. So the hand is very important in robotics. Actually, in robotics, I would say is the only open research that we have, because right now we buy arms. So there are many companies producing arms, like, I don't know, I can mention many of those. You go around and you buy an arm, okay? And then you have to design your end effector that works in industry, in food manipulation, in logistics, in pharmaceutical industry, and you specialize the end effector according to the object that you want to manipulate. No? So most of the crowded research areas in robotics is in the end effector design, not in the arm anymore. Okay, so it's very popular now in robotics. And again, even in robotics, you can think about, so even the manipulation of 2 arms on the same object, like whatever is the object. Okay, for example, my pocket. So if you have 2 arms manipulating the pocket, is still the mathematics of the grasping and the manipulation. But hands does not mean robotic hands only. It means also human hands, no? Because as my colleagues that was greatly introducing my talk before, I am quite interested in the quality of life improvement. And one of the typical problems that we might find in our life is a stroke. When I will go towards the years and I will become very old, it's it's likely that I will have a stroke that I will probably solve. I mean, when I will be 100 years old, for example, then, and it's very likely that I will have issues to my hand. No, maybe probably people that cannot manipulate any more objects because of a stroke that just reduce the control of your hand. So rehabilitating the hand through robotics is an important subject that I love. And knowing the biomechanics of the hand that is very similar to the mechanics of an anthropomorphic robotic hand, you can do things. So knowing the biomechanics of a human hand is the same complex mathematical complexity of knowing the mathematics of a robotic hand, and we are dealing with the human hands because we want to help people with the stroke. Of course, hands are very important in humans, no? If you count the number of joints that control, I mean, you can count the complexity of a human hand by counting the number of degrees of freedom that you have to control. For a finger, for example, you have this joint, so you have 1 parameter, and then you have 2 other joints in this articulation here. So you need 3 parameters to control 1 finger, right? So basically, a human hand needs 3 plus 3 plus 3 plus 3 plus 3, so needs 15 parameters to be controlled. This means that while I write or I do something with my hand, I am controlling 15 and more parameters in my brain. Now, if you look to your body, my body is more or less the same complexity of a hand. No, this can be thought like a palm, right? The arm without the hand, the arm from the shoulder to the wrist is exactly like a finger. So this is, you know, this joint, the same, and the shoulder that has 2 degrees of freedom is exactly like this joint. So the finger is exactly like an arm, right? And the leg is exactly like an arm, right? Okay. In fact, when you, and the leg is exactly when you simulate walking, you do something like this. So what I want to say is that a hand is like a body, because this is a sort of a, you know, chest. These are the 2 fingers. These are the other 2 fingers, the 2 legs, sorry. And this is maybe the head is the thumb. So basically the body is like a hand, a palm, 2 fingers, the other 2 fingers, and the thumb. So the complexity of the body in terms of a number of parameters that you need to control is very similar to a hand. So it's something like in our brain, we have the complexity of 3 hands, the 2 hands plus the body that has the same number of parameters that a hand has, okay? So what I want to say is that most of the variables that our brain need to control are in the hands and not in the body. This is the reason why when someone has a stroke, so it's very likely to have an issue on the hand, because on the paretic hand, because there is a large area in the brain that is devoted to control the hands. So controlling the hand, understanding the hand, for sure helps us building hand effectors, very smart in robotics, help us to support humans that have a paretic hand, okay, and help us to control a complexity that is very important in our body, that is the control of the human hands. Of course, it's not only the thing, so we said robotics, we said flesh and bones of the humans, plus we said something virtual, no? Having controlling the, so virtual reality, metaverses, augmented reality, has a representation of our body in the digital world, okay? And one of the main issues in the digital world is to represent the digital twin, the digital body, but also the digital twin of the hands that manipulate the object around. I'm not sure if I can do something more dynamic with you, but if I take the Zuckerberg metaverse presentation, I think it's in YouTube somewhere. Zuckerberg metaverse. Let me see if I can see. I think this one. Not sure I can. Let me see if I can find it here.
Apri il tuo negozio online e vendi i tuoi prodotti su Facebook e Instagram con Shopify, la piattaforma di...
It's time for us to adopt a new company brand to encompass everything.
Okay, look here. This part is talking about, this was the main presentation of the metaverse. And you see already here, I will show you it full screen. This researcher is talking about the relevance of the hands in the metaverse. Have a look with me in just 1 second.
Mixed reality experiences on Quest 2. Now, you want to tell us more about the Presence platform?
Yeah, we've said before that realistic presence is the key to feeling connected in the metaverse. And the Presence platform's capabilities are what's going to deliver on that promise. Things like environmental understanding, content placement and persistence, voice interaction, standardized hand interactions. In fact, let's start with hands. I mean, the human hand is an engineering marvel, and bringing hands into VR was no easy feat. It required a lot of collaboration against product, design, research, but we continue to improve that product, finding new ways to navigate with gestures and interact with VR. So today, we're introducing the Interaction SDK, a library of modular components that will make it easy to add hand interactions to your apps.
That's all. So what I want to say here is that the mathematics, the methods of understanding the hands is something crucial in the metaverse, in the virtual reality, okay? Because if you think about, think about also to our body, no? Okay, of course I cannot, maybe I cannot see because if I am blind, okay? Maybe I cannot hear if I am deaf. Maybe I cannot speak if I am some disease. But if I don't have the hand, for some reason, probably I cannot eat. I cannot do the very basic thing. So it's more likely that I will die if I am alone and if I don't have the hands, because I cannot, do many things like eating, for example. So what I want to say is that the hands is very important because it's the real interface with the environment, is the real organ that allow us to change the world where we live, to build computers, to build the tools, to design, whatever are the tools that you have in your mind, that has been done by hands. And also the role of the thumb that is crucial, that seems to be trivial, okay, but is crucial, make a big difference between us and animals that don't have the hand. And this is the reason why humans are the mammifer that is dominating the world, because became more intelligent because of the hand. So what I wanted to say here is that we are quite obsessed by the concept of the hand, but the concept of the hand is general enough to cover many areas in our world that goes from robotics to metaverses going towards the human hand for rehabilitation and whatever. What the hand does, the hand manipulates things, but also touches things. So we are, in general, when I am manipulating an object like this, like this bottle, at the beginning I touch it and I understand something about the bottle, and then I manipulate it. So we have inside our marvelous design of engineering design of the hands, we have technology, biological technology for touch and biological technology for manipulation, okay? So we love to tell the story about our lab as an expert of technologies of manipulation and technologies of touch, okay? So this is our common ground. I will start with the technology for touch. That is something a little bit more different from technology of manipulation we are typically used to think about. Okay. Well, this is a video of Bezos that is using both technologies.
Please
Of course, what you have here, you have an arm that, as I said, we typically can buy. This is a universal robot arm. There is a hand, okay? So technology for manipulation here. So then there is technology that is using on his hand, both to control the robot, but also to perceive the hand action on these objects. No? So he's able to teleoperate the robots and to feel what the robot is doing across this other technology on his hands. So here we have technology for touch, that are the tactile sensors on the robotic hand, plus we have technology for touch that are actuators, that are stimulators, that apply stimulus on the hand of Bezos, replicating what this sensor is measuring. So the technology for touch is not only tactile sensors, but are also motors, actuators, that stimulate the skin of the human according to what the sensor is measuring here. So there is a map from the digitalized touch here and the actuated stimulus on the human hand. So this is a scenario of teleoperation that, I can go a little bit farther here.
I could not do that.
So what I want to say with this teleoperation is that, maybe we can, I don't know if we can discuss a little bit together. So where this teleoperation scenario is important for? What do you think? This is for just a game, no? This was just a demo, whatever, right? But in general, where this teleoperation scenario is important for? Maybe I can talk with you if someone wants to just talk with me in the audience, some student or even some colleague, just to talk together about it. Professor Aparajita, can I talk with you?
Teleoperation can be useful in medical robotics, surgeries and all that.
Say again, sorry, say again.
Teleoperation can be useful in medical robotics, performing surgeries.
Yes, but medical robotics, why? Medical robotics is, for example, teleoperation is important when there is a scale factor, no? So open surgery, it means to open the abdomen and put the ends of the surgeon inside, right? So if you want to scale down the hand, of course you cannot put directly the ends of the surgeon, and you have a very little surgical manipulators that goes inside the body to do micro manipulation, and you have your hands outside. So this teleoperation scenario is very important when there is scaling. So when you want to operate to a smaller scale or even to a larger scale, if you want to teleoperate a robotic arm with hand on the satellite or the space station, for example, then you have a larger hands, and then you want to do something teleoperate. So when there is a scale, right, a scaling, or when it is dangerous, for example, if this is the disaster of, I don't want to talk about military application because I simply hate the war, and I hope that these stupid things that is happening in Europe will end very soon. So more than stupid, I would say crazy, whatever. By the way, if you think about the disaster in Japan, Fukushima, no, the nuclear disaster because of the quake. Then, of course, actually there were many operators dying because of the radiation in the nuclear plant, but they sent a robot inside the nuclear plant, and the operator was outside, far away, and the robot was manipulating the valves, opening and closing the water flow and whatever was there. Actually, to be honest, they didn't work well. One of the main reasons was that the radiation affected also all the electronics inside the robot. But you can think about dangerous area where you cannot go with your body, and you send a robot, even if the scale is similar. Another application that can be think about is for example, is telepresence. No, if I want to stay here, and suppose that I am a doctor or I am an artist, and I want to show you something with my hands at your desk, that I can teleoperate something and giving the lecture by showing what to do with the hands for a typical surgical operation or whatever. Okay. Right now, I cannot say too much here because it's it's patent pending, but I'm working a lot also in the metaverse interaction paradigms with robotic manipulation. Okay, do we have question up to here? So, just to summarize, what I wanted to say is that in order to be in this global world, in order to be, so I live in Siena and I live in Italy. So I'm not living in Palo Alto or in Shenzhen in China. So this means that I'm not in the center of the geographical center of the world where technology is growing. So if I want to have engineers coming from China and the US to talk and collaborate with me, I have to be very specialized. So very focused on something. Otherwise, there will be a general engineer somewhere in China or somewhere in California, or that will be able to do the things that we could do from Siena. So if I want to live in Italy and to be crucial in research, I need to be focused on something, which means obsessed about something. And our obsession is technology for touch and technology for manipulation. Okay? Let's start talking about the technology. I mean, here in this picture, we see technology for manipulation and technology for touch. I will start talking in the first part of my lecture about technology for touch. It is called haptics. Okay? We will talk about haptics. So haptics means, from the ancient languages, means touch interaction. So touch, what touch means? So touch means, so I'm here talking about tactile interaction, but I'm also talking about something more interesting, and I want to talk about the colleagues that are doing AI there, and I'm also doing, in some sense, AI as well. But AI are done by two main things. One is the algorithms, machine learning, deep learning, that allow us to interpret data in some way. The other face of the medal is to have technology to acquire data. No? In order to manipulate data, we need to have data. And to have data, we need to have sensors. We need to have technology that digitalize the data. So we sell our research skills also in the AI world by saying that we are inventing new technology to gather, to acquire, to get tactile interaction data. So when I mean, just to give you an idea, no? When I interact with my pen, okay, and when I write, maybe I have a lot of data of this kind of interaction, right? And maybe this data can be associated with with the prediction of some Parkinson, for example, that is much more visible probably in manipulating the pen while writing, and not only in the tremor. Or maybe I'm working in the agriculture and food industry, and the way I manipulate the food while getting the grapes or whatever, it's also important to understand the level of, the level where the food is, where the fruit is, if it's good to get at that time, or if I have to wait more weeks, for example, by, for example, measuring the compliance or the mechanical impedance of the fruit, of the apple. I can understand if it's good to get the apple now, or if I have to wait. And digitalize the data can be important. If I'm a doctor, and if I want to teach all of you some palpation technique, no? In order to recognize the tumor in the breast, for example, maybe I want to digitalize the action of touching my, imagine to have the nodules, the lymph nodes at the base of the neck. No, I'm digitalizing now. If I have a technology on my finger that is able to digitalize this interaction, I have more data. No, if you think about televisit, this is also something that we are working now a lot. For example, is the televisit. No, televisit means telemedicine. So patients are not going at the hospital anymore because of the corona, or because of some other reason. And I want to, sorry, there are messages in the chat. Should I have a look too, if it's a message for me?
Yes, there are a couple of
okay. Yes, so handling radioactive and toxic chemical and substance in lab environment, very good, very good. For example, industrial application, I would say even more, pharmaceutical industry. So in industry, automotive industry, people say that robots are dangerous for humans. In vaccine industry, in pharmaceutical industry, people say that humans are dangerous for humans, because when a human do a vaccine, the human can be contaminated, because I'm touching something outside and I'm the worker and I go to do the vaccine. And the sterilization is a little bit difficult with humans. If I'm a robot, it's very easy to sterilize me. And it's very easy to keep me in the sterilized, in the clean environment for years, because I don't have to go outside. So in pharmaceutical industry, humans is dangerous for humans because of contamination. So people love to have robots in industry, in pharmaceutical industry, right? While, so this is the, I don't know if I get you the concept, but in typical automotive industry, for human robot collaboration, human says that robots are dangerous for humans, safety, blah, 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 blah. In the pharmaceutical industries, people say that humans are dangerous for humans because they can easily contaminate the vaccine. So people like a lot robotics. So in my opinion, robotics is very, very crucial now in pharmaceutical industry. This is just to answer, to give you. So you like this interactive way of doing the keynote? I hope so. Okay, good. What was it? I was saying something about, okay, thank you. I was saying something about, I missed myself. So televisit, teleoperation, we are working a lot about that. So in televisit, I can be the doctor. I can say, okay, good. Tell me, how do you feel? What's going on with your, I don't know, suppose that I'm visiting some tumor patient that has been operated by me and surgical operated by me and blah, blah, blah. How do you feel? Tell me something about me, about you. Let me see the nodule that I operated. And then I see, I want to touch it. So tactile technology is important to remote palpate the base of the neck, for example. Then I can have something. What we are doing is something completely different. So the patient is wearing a ring or a thimble, is touching itself, and the doctor, and is digitalized this interaction. And on the other side of the world, the doctor is feeling on his hand what the patient is touching itself. Okay, so this is very, very interesting. So there are many, many applications that goes far beyond the technology for virtual reality and technology for augmented reality, and touches the quality of life for us. Okay, so let me start in the first part of the lecture with the tactile technology. Okay, so, and I will tell you also a little bit the story why I was very, you know, I was really surprised by this technology. So why haptics technology is very close to robotics. And sorry, for people that is doing AI, this kind of technology is crucial because we can gather new data that we can enrich also, for example, even for e-commerce. The way I touch, so suppose that I want to go to buy something, you know, a bag, no? Then the way I touch the bag in the store can give some information about the product, no? So touch is really, really important. So why touch is very related to robotics, and I will tell you why I got in love with this technology. Okay, so touch means, so when I touch the phone here, it means that I apply a force to the phone, and the phone reacts with a force that is equal and opposite, no? Like in this case, I am here touching just a second. I want to be as interactive as possible with you to involve you in the okay, here in this case, the hand is having a tool, is applying a force that goes inside the ball, and the ball is reacting with a force that is equal and opposite, no? So this is a kind of, this is the touch interaction. So if you want to make it virtual, okay, you need to virtualize the ball with a virtual ball like this one, that you can see maybe with an helmet. So you have an helmet in front, you have, you know, the whatever, the Oculus helmet, like here, no? You have your helmet, and in the helmet you can see the virtual ball, okay? So you can change, you can see the virtual ball here. But in order to feel it, you need a robot, no? The robot should apply on your hand through this tool exactly the same force that the real ball would apply on this pen if it was really here. So you want this robot to generate this force that is not generated by the reaction of the ball anymore, but this robot here that simulate the reaction of the ball. I don't know, is it clear why robotics is important for tactile interaction with this example? Because robotics applies forces. Touch is force interaction, and you need a robot to apply a force somewhere to simulate the presence of an object. Okay? And again, this is just to give you a story, a little story that helps me also to create a more interactive lecture. Is when I was a postdoc, I was at MIT in Boston, actually in Cambridge, and there was I was doing robotic manipulation. I was playing with a robotic hand, and in the desk close to my desk, there was the guy who patented and invented with this professor this device that is called Phantom by Sensible. Now I think that the company does not exist anymore, but was the first, or has been bought by another company, but is the first company that invented this haptic technology, and it was really crowded. So I was really impressed by the number of people that were going to visit this PhD student in order to see what this invention was able to do. There were artists going there because they wanted to play with some digital sculpture. There were people trying to write in a digital world, or doing, all the things that you can imagine. So I was really, really impressed, and I said that, it's something that I want to do there in that area, because I'm also quite personally quite attracted by humans more than just iron, metal, and wires. So I like to have humans around the technology that we develop in some way, because I think, even my course that I will teach is human-centered robotics, because there is always a human in my dream, in my research, in my vision. And the tactile interaction, so creating machines to interact, to simulate the touch, is something by design for humans. So the human should be there, no? So the real object of this experiment is the human that should feel this sphere like a real one, okay? So this is the reason why I was really fascinated by touch. At that time, when I started working about touch, then I said, I was doing grasping before, no? The story of my life is that I started doing robotic grasping, and then I got into this area. So I was doing this, no? Grasping, manipulation with robots, whatever. I am a more model guy than technological guy. So I'm more expert in modeling of this aspect and creating, new ideas, even in terms of devices, more than a specific technology. And this is also something that I want to tell you now. And even most of the Indian excellent technological school are focused on, even theoretical aspect, modeling. Most of the best mathematicians that now are leading the multinational, I can just mention two of them. I wrote a paper in is one of my co-author, a few paper. His name is Shankar Sastry, and he's in the American academia. He was doing robotics. He wrote a a famous book on robotic manipulation. He's very famous. And I have the honor to write a paper with him, and he's very famous because a lot of models in his brain. And even now, the CEO of Microsoft, who is changing the world of Microsoft, is an Indian guy, Nardella, with a lot of methods, in my opinion, in his brain. So in some sense, now it's the era of methods and abstraction in some sense, because technology goes so fast. So, you know, right now we are dealing with the metal of robots, but maybe tomorrow this robot can be done by biological material. Who knows? No. So even if technology changes, there is something that we can keep over the years, that are the mathematical foundations, the theoretical foundations, where the technology builds on, you know, grows. So we should be able to, I mean, this is at least my vision. We should be, my lab should be able to deal with the technology for touch, no matter of the nature of the technology that is in this year. So if in 10 years technology changes, we would like to play a role also in that area. Of course, we cannot live without technologies. So without you know, people working on the specific servo motors, on the specific cellular reaction for a biological machine, we cannot do anything. But what I want to say is that the technology goes much faster than methods. Okay, so even if you are doing pure technology, trying to keep an eye on what resists over the years is an important element of scientist and professor of the future. Okay, so we were obsessed by, you know, this is the story. So this is the touch. This is what I saw in the lab. This is what I was doing. And I said, oh, I want to do something completely different. I want to invent something that let me able to do multiple contact interaction with the real objects. Because the guy here invented something interesting, but was, you know, just a simulation with like a tool. So he was able to simulate the pen like the surgical interaction with the tool, pen writing, sculpture, but still it was a touch tool mediated, you know. But sometimes when you touch your face, when you grasp a bottle, you are, you know, your fingers are directly interacting with the object. It's not mediated by a tool. Okay, this is very popular in surgical robotics training, not in direct interaction. So we started doing something. The first thing that was easy to do for us was in the upper part. So I took a robot that was doing, so this is a robot by, this is actually is an existing company. This one is called it's fourth dimension. It's still existing. It's very popular in you know, in the world that is doing optics. And they invent this you know, this kind of parallel structure to do the so at the end of the surgeon you have the simulation of the forces like the end that was operating. It's a parallel structure. So I took two of those. I removed. Here there is a ball. Can you see the ball? Oh, sorry, here. Can you see the ball here? I mean, you see the ball here? That was the ball that was manipulated by the human. I removed the ball, sorry, and I put some thimble to have the index and the thumb. So I had one robot for the index, one robot for the thumb, and I was doing manipulation in VR by using thumb and index and these two huge robots, but was not, not interesting at all. Not interesting at all, because why was not interesting? Was not interesting for two reasons. One is that it was too complex. A robot for each finger. Yes, I can simulate this by putting a robot to each fingertip. So in this case, I should have 1, 2, 3, 4, 5 robots. Really complex, too much complex. You have questions? You have comments? Okay, no, maybe not. So then we started thinking about something more complex, that is the exoskeleton. So we developed this exoskeleton that was able to apply forces at the fingertips by using these motors on top of the fingers, and we were able to simulate the interaction with this. But was not impressive. Exoskeleton. The design was impressive, in my opinion, because it was underactuated 1 degrees of freedom per finger, 3D printed, whatever. Okay, but was super interesting. Why was interesting from here to here? Can someone? What's the difference between this setup and this other setup? Even a quick answer in the chat can be interesting. So the big difference is that this was grounded setup. This is a wearable setup. I can go around in Jabalpur or in Siena or in Rome, wherever, and I can still have my wearable device. If I use this setup, I'm confined, I'm constrained in a certain environment. And this is also a big element of our research as scientists. Believe me, it's unbelievable. It's unbelievable how people want to go to have technology to be wearable. So there is a sense of freedom when you have a technology on your body with you, that you cannot, it's unbelievable. Think about the phone. Think about the phone. Many years ago, there was the grounded system, in Italy is this called cornetta, there is the phone that you have to, do you remember, no? The phone that you have to answer. It was in a room of our house. Are you okay? It's clear, this concept? I'm talking about this old system, right? This old system 1, no? So it was much different from this one, much different from this one. And the big difference was not about the shape or the LCD. The big difference is that to phone Professor Aparajita, I had to go in a specific room of my office or of my house and to call her. So my body was constrained in an environment. Nowadays, I can go around and I can call Professor Aparajita and talk about the GIAN course, okay? And this is a big sense of freedom because I can do this wherever I am and I'm not confined in a certain environment. So what I realized is that whenever you have a sense of, limitations of your body because you are asked to go somewhere to do something, it's less powerful than having the wearable technology. So the other term we are really obsessed by is the concept of wearability. And this is the real, this is the patent that we created. Is the first super highly wearable mechanical, mechatronic, robotic device that is able to stimulate your skin by simulating the presence of a virtual object. See here, a little robot with the 3 motors on top of it, a plate here that can simulate the interaction with this virtual world. Have a look. You see here, as soon as the virtual finger touches the ball somewhere, you have a tangent plane. This plate at the fingertip orients as the tangent plane to the sphere, because you can control the pan and tilt of this structure, plus you can squeeze the fingertip by letting the sense of pushing on the ball. Okay, so 3 motors: pan and tilt of the plane, of the plate, plus squeezing against the base of the finger. Very important, very important. So this was a first wearable design that we developed in Siena. We patented it. And we created this super wearable design. Then I also have to give you, for my colleagues, scientists in the room, is that before I was, I don't know how familiar you are with the IP, intellectual properties, but it was not my case at the beginning. So it was only focusing on papers, on scientific papers. That's it. Boom, 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 boom. Scientific papers only, you know, publish or perish. And then when I was thinking about, oh, okay, nice, this idea, maybe it's nice to patent, then it was maybe too late, because the paper was already out or published in some conference, and it was really difficult to get, you know, the time. You don't have to publish anything before patenting. After some experience, you know, I'm starting patenting a lot. Now, I think that in the last few, you can search on Google Patents, my last name, just put double T and double Z, because it's a little bit difficult. Then you can see how many patents and I was presenting over the years. The patent is very important, because when you have a company that want to invest on your ideas, if you have a patent, the company say, okay, good, I can put the money on it, because if it's successful, then there is at least an intellectual property I can use if someone tries to copy me, okay? If there is no patent protection, the industry, the multinational, will be difficult to put money on it, because it's already on papers. So anyone worldwide can take it. Of course, there are ideas that should be, I mean, once you have the patent, you can decide. The patent does not cost too much. The patent, just to give you an idea, the patent here in Italy, including the initial part of the patent, including the consultant that write it in the patent mode, patent language, costs about, let's say, 4,000 euros, more or less, which is not too much, no? So you can invest on it. After you can decide if you can open the patent and have an open project to help people, for example, poor people doing something, or if you want to invest on it. Look that the investment is not an issue of getting money in your pocket, because in university you reach a prototype level that will never go on the market unless there is a huge investment from the industry for the engineering part. For example, this idea now is a product. I will just show, but I will go here in a moment. Is a product like this here, okay? But to go from the prototype to the product. There was a lot of money and a lot of time and a lot of expertise that goes far beyond the expertise that we have in our laboratories. So having money from private or public, but even, we got money from the government about our patents, but still we need to interact with the private company, because the private company have the expertise of making a product, because the university is not designed to make products. University is designed to make ideas and to show proof of concept. And then there is another something else, someone else that takes this idea and brings the idea as a product. Now, if I want to have this product helping people in South Africa for telemedicine, I need to have this development. Still, I need a lot of money from privates or from industries to make this engineering part, because I'm not able to do it. So if you want to scale, you need something else that goes beyond your lab. Okay? Do you have questions here? So I can just take a rest. Can I ask you, my colleagues, if you like this, not only technical keynote? No comment? Voice comment? How do you control the motors? I will tell you as soon as we go there. It's just an open window on that. It will be also part of the class of the next days. Okay, let me see if I have another question in the chat. No, it's not only mechanical pressure, we do also temperature and vibrations, but also we'll go there in a moment. Okay, keep going here. So basically, we wanted to develop, we wanted to scale from something wearable to something that is highly wearable, something that is similar to the smart band that we wear when we go jogging. So this is the reason why we developed something very light and very wearable like this. So a few words on the control. So there was the the inner loop was a position control for the three angles of the motors. So you have three motors that are controlling the three angles of the parallel structure. So QD are the parameters of the angle here at the servo motors. And then there is, of course, a position control. Then you have an inverse kinematic. So the reference position is the position of the plane in 3D. That is the pan and tilt orientation of the plane, plus the position of one point of the plane. That is P is the 3D position of a point of the plane. Psi and theta are the angles. Then you do the inverse kinematics from the plane here, this plane here, to the angle of the joints, and then you do the control of the plane. And then, of course, there is one big point here. Are you with me, guys? And colleagues, guys, from the students and colleagues from my scientist friends and colleagues. So one big issue here is that you need, in this scenario, to track the human hand, because one of the main issue in haptics is body tracking, because you need to understand where the hand is in the virtual reality. So you need to digitalize the position of the hand to understand the relative position of the finger with respect to the object, to generate this virtual force that should be applied to the robot, okay? How do you do the tracking? Well, the tracking was very easy in this case, right? Because for the old school, for the old robot, was very easy to track the end tip, because the end tip was attached to the robot, no? And since it is attached to the robot, I know very well where this position is through direct kinematics, because I know the model of the robot. I know the angles. I can immediately find the coordinate of the end effector. Clear? Very good. If you go wearable, you need to have a tracking system that should be different. It can be done either by cameras, that's okay, but can be done also with some, this is a prototype in my lab, and you see the roughness of the prototype, and this is just to show that we are not asked to do very, engineered and product-like design, or we need to show the concept. For example, here we were putting these blue boxes where we were using the IMU, the inertial measurement unit, that even the ones that you have in the phones, to understand the orientation of the link. Then you have a model of the hand, and by using a Kalman-like filtering, then you can model-based filtering, you can get the position of your fingers. And the position of your fingers is very important in order to interact with virtual reality. It's very important. And this is, for example, an application of our algorithms. That is even an open library that is called Gesto, where we show the tracking. The penetration is not an error. The penetration is mandatory for haptics, and I will show you in the lecture of the next days. You know what I want to tell you? That is also an important aspect here, is that before, people was doing, here there is a very advanced noise cancelling algorithm. Why? Because the IMU in the blue boxes are very sensitive to the magnetic field direction of the earth. No? Very sensitive, okay? And you have to stay far away from metal, no? If you stay close to some metal, then the magnetic field changes the direction because of the metal that attracts the magnetic field, no? So the magnetic field is directed towards north and south because it's free. But if I take something metallic like this microphone, then if I put an IMU, the IMU feels this part. And even more, if here there are servo motors in the red timbers, there are servo motors. The servo motors have the magnetic element inside and even metal, and this makes error with respect to the magnetic field. So the blue IMU were full of errors because of the metal part of the motors that are important to stimulate the pressure of the fingertip pad. And so we built in this paper a very nice noise reduction model-based algorithm to get rid of the disturbance of the magnetic field. I hope that I gave you the idea. Maybe can we take just the first break? if you don't mind.
Yes, yeah, Professor. Thank you so very much for such a nice introduction, giving an overview, everything. We can have a small break of how many minutes, Professor? You would like to have a 10 minutes or 5 minutes, whatever you say?
10 minutes would be nice.
Pardon?
10 minutes.
10 minutes, okay. So we will be meeting participants. It's a 3:26 here. So we will be meeting at 3:36. Meanwhile, you can relax, have a cup of tea or coffee, and then come back.
Madam, one thing actually.
Yeah, please.
Can we have a screenshot of?
Oh yes, there is a screenshot that is a requirement, Professor. So we need to we need to have. Can you please unshare your screen, and we request all the participants to please put on their videos. Thank you. May I request all the participants to put on your videos? So Vijay, I hope you can take.
Yeah.
Participants, please requested, please put on your videos. I hope you can. Tanuja, you are here. Professor Tanuja is another person who is working in robotics, and especially she's working with Vijay on rehabilitation robotics.
Good.
Yeah. So both of their students are.
I'm just taking the video.
Thank you.
Just wait.
Yeah, thank you all.
So we are many now. We are, I think, 42. I think that we reached also 45, 46 now, which is very good. Thank you for attending.
Yeah. One of my former student who is now in faculty in another IIIT, Indian Institute of Information Technology, he is also present.
Good, very good. Let me also say that right now we have, I have many, I mean, for sure we need to invent a collaboration that among us that does not need to stay directly here in Italy, okay? Maybe we can imagine students working on the same subject by moving from one lab to another lab, okay?
Yes.
But let me tell you that we have, especially my lab, both in Siena and Genova, is opening a lot of positions from PhD to postdoc positions.
Okay.
I recently won 3 European projects, very huge, and something very important is happening. So there will be at least 10 open positions in my lab from PhD and postdoc. But this, I mean, this is not the only way to collaborate, because I'm imagining to have common projects and having students coming, I don't know, 2 weeks here, and then staying 2 months in your lab, and then, you know, something more integrating than just applying to my lab position, okay? Because we can also pay for travels and whatever. By the way, we have these many opening positions. So if you professors and colleagues are interested in knowing more for your students, please get in touch. It will be a real pleasure and honor for us to collaborate with it.
Thank you so very much. I'm sure that many of the participants and students here will be interested. Please write to us. We will definitely connect you to Professor.
Thanks a lot.
So we'll have a small break. So 3:30, so 3:40. Shall we meet 3:40?
Yes. So 10 minutes I will be here, okay? I'm just muting and closing the camera, and I will open it in 2 minutes, okay?
Sure.
Okay, good. So if you share the screenshot, it will be great, even via email. Thank you.
Yeah, I share on email.
Vijay, I have paused the recording. Okay, so you can start. Please remember to start.
Yes, madam. Yes.
So participants feel free in asking questions and writing. You can write on the chat box. You can raise your hand so that we can make this session interactive. And we thank you for your interest in the course, and you have been asking questions that makes the sessions more live.
So I'm ready.
Yes, Professor. We are ready. We are also ready. Thank you.
Okay. Okay. Where should I go? I should share the screen.
Yes.
Okay. So you sent me the picture via email? No, via message. Not really. Okay. Well, okay. So going back to the, I think that you can see my screen, right?
Yes.
Yes, we can. Yeah.
Okay. So here we are. Looking to the main principle that we were discussing before. Now, so we moved from this wearable idea, okay, for touch. We moved from a grounded situation like this one to something that is highly wearable like this other one. So if you want, sometimes we always do parallel discussion reference to what happened to the other modalities, right? Oh, sorry, even this is a robot, because this is a parallel robot, very small but parallel robot. Okay, this one is a parallel robot that is small and wearable. Okay, so we went from the situation of going from a robot that was designed for grounded interaction in haptics to something very wearable, still a robot, where in this case, in order to make it lighter, the plane was moved by cables here. You see the cable, and then we had the pulley here that was just taking the cable, reducing the length or augmenting it, and we were controlling pan, tilt and squeezing because of this three cable. For example, the modeling here was really important because the model goes depends also on the compliance of the finger. By the way, going from grounded device to wearable device is exactly the same paradigm shift that we had years ago for music, where we had the speakers, okay, that we have in our room to listen the music in our houses, to something that was highly wearable with the headphone. No, I don't know if you remember, but one of the first, actually the first patent in this field was by Sony, and Sony Walkman. Probably some people remember the cassette, no, where the music were recorded on it. But the big paradigm shift was to have the headphone. So the Sony invented for the first time the headphone, right? So to listen the music while walking. So the concept of wearable. And this was actually really a technological push also for music, because of course, when I have the speakers in my house, I had the ability to have all the long planes, the vinyl discs, no, to my house to listen to it. When we went with the headphone, we had the problem of having all this data with us. So we had to start thinking about the space occupied by data. And so they invented at the beginning the analogic recording with the cassette. And then we had the hard disk that was popular with the mechanical hard disk and the digital sound with the all the music portable device that are using the hard disk and also the SSD. Most of that technology came from the paradigm shift of going from house to wearable. Very important. Wearability is very important. Now, if you are passionate with music, you know that when you listen to the music, there is a big difference when you use the headphone. What's the big difference? Can someone tell to me? From listening the music through regular speakers and through the headphone, what's the main, what are you missing typically?
There's no interference, if I'm not wrong.
Yeah, but you are missing typically some frequency also, no?
Yes.
Which one? The bass. The bass is typically less powerful than the high frequency part of the sound, no? Because there is not enough room to move things that replicates the sound at a low frequency. Do you agree with me?
Yes, yes, I do, sir.
Okay, so what I'm saying is that because of wearability, we are missing something in the experience. And this is exactly what happens in haptics. So from here to here, we are missing something. And I will tell you immediately what we are missing. Maybe I want to show you I wanted to pin myself. I don't know. I mean, can you see me?
Yes, sir.
Okay. So what I want to say is that when you touch, look to this experience of touch. No, I'm touching this poster here. No, look to my finger. At the beginning, I'm feeling the touch by using the receptors in the skin. No, at the very beginning, the receptors that are active are those in the skin, no, that measure the force interaction. Then, at a certain point, especially when I push more, the receptors that are perceiving the sensation of touch are those that are in the muscle and in the tendons. So we are able to perceive the touch because of the skin receptors, but also because we have sensors either in the tendons or in the muscle. So as soon as I apply more forces in the interaction, I have a muscle stretch and a tendon stretch that is perceived by these deformation sensors. Is it clear? Right?
Is it okay if you can repeat it?
Okay, so we have two kinds of, as humans, we have two kinds of receptors in our body, okay, that perceive the touch. The first set of receptors are in the skin, in the derma, no? So if you look, if you don't apply too much force, then the skin receives the force interaction, okay? When you apply more force like this, okay, the skin probably saturates because they push too much, and you are feeling the force by using the sensors in your body that measure the stretch of the tendons and the muscle. So we have sensors in the muscles and in the tendons, okay, that as soon as you stretch the muscle and the tendons, the sensors measure this deformation, okay?
Clear, sir.
Okay, so this is called the cutaneous perception, the receptor of the skin, and the muscle, when you push, are called the kinesthesia. So you have kinesthesia, muscle and tendons, cutaneous, that is the receptors of the skin. Now, in this experience, what are you missing?
So we are missing a position and the surface of the object.
Yes.
Connecting.
So we are missing the sensation of the, so we are not stimulating with this device, we are only stimulating the skin, right? We are not stimulating the muscle and the tendons, because you have a device that only pushes on your finger, right? So you are only deforming the skin. You are not using the muscle and tendons receptors of your body, okay?
Yes, sir. Yes.
So this means that like in audio, when we go from here to here, we miss the low frequency bass of the sound. When we go from here to here, we miss the muscle and tendons perception that is called kinesthetic perception, and indeed is the low frequency part of the sensation, okay? So because of wearability, we are missing the low frequency part of the interaction. Now, someone can tell me, okay, look, wait a moment. So you are missing something that is important or not? So in this experiment, so we are using only the cutaneous perception, right? Okay. In this experiment, there is an healthy subject that has been anesthetized at the skin level, and she is not able to perceive anything with the skin because of the anesthesia, okay? For example, we have used the spray that make it cold, okay? Even when you play soccer and then you get the heart, you can use some spray to anesthetize the part. So we were using the spray to make it anesthetized. Actually, I was not doing this research. This famous neuroscientist from the north of Europe, Johansson, was doing it in 2005. So this is an healthy subject where the skin was completely anesthetized, and she had a task that was to move the object from the box to out of the box, and she was not able to do anything because of the skin anesthesia. So she was only using the muscle and tendons perception. She was not able to do it because of the skin anesthetized. This means that in the skin, there is a lot of information. So even if we are missing the muscle and tendons, the skin part is still very, very, very informative for the interaction. So even if we miss something because of the low frequency absence, because of wearability, is still something very, very important here, okay? Because we can do many things. Well, because of this wearable part, we were able finally to do the multiple finger interaction that I was really interested in. Okay, this was the real, the multiple finger interaction. Actually, it was the initial dream I had in my mind in order to do the multiple finger interaction. This is something even more advanced. So in this paper, we were showing the deep integration between the algorithms and the skin stimulation. Another important thing is that is the concept of wearability. Maybe I can still talk with you because I like to have more interaction. So how we define wearability? What wearable means for you? Give me some answer, some comment. So when I say wearable, how do you define wearability?
It fits into our body, like not into our body, onto our body, if I'm not wrong.
So it fits on the body. So it's something that you can wear. But for example, imagine that I have a broken elbow and I have a cast, a rigid cast, no? It fits the body, no?
Yes.
But is it wearable? I don't consider it wearable because it stops the function of my elbow. So I can use I can call this shirt wearable because I can still move my body freely, okay? So I consider wearable something that does not prevent any motion of your body. Your clothes don't prevent any motion of your body. So you are still free to perceive everything. Good, very good. So this is my definition of wearability, my interpretation of the wearability. But is the only thing that we do with the body? We move the body? No, we also touch things, especially with the finger, okay? So if I put a device on my thimble, like, what is it? Like this one, okay? Then I can move the thumb, I can move the index, but I cannot perceive it, right? I cannot feel the real object because there is this plate, okay? So in order to have this feeling on the fingertip, we moved the design from the thimble design to the ring form factor concept. And we developed another device that is here explained, a ring device with, in this case, 2 servo motors, because 3 was difficult to have there, okay, with a belt, okay, that goes through one motor to another. And when these 2 motors rotate in opposite sense, you generate a normal force on the base of the finger. And when you want to generate a tangential force at the base of your finger here, you know, then you have to rotate in the same direction the 2 motors, okay? So with the 2 motors at the base of your ring, you were able to stimulate both normal stress and the lateral stretch. I call it normal force and tangential forces at the base of your finger, while having your fingertip completely free, okay? This is, for example, the demo. In this case, the guy was able to type while doing the virtual reality experience. So there was no limitation in using the fingertip perception. So for me, the ring is more wearable than the thimble because allow you to move the finger, but also to perceive with the fingertip pulp, okay? So wearability means to not limit the motion and to not limit the perception of the environment, okay? Of the environment. Actually, this was the, so now tell me something more. If I am in virtual reality, right? Pure virtual reality, which means that I have an helmet like this, an Oculus, no? Whatever. So then, you know, I'm living in a virtual world, no? So in a virtual world, everything is digital. I don't need to touch real object at all, because all the objects I interact with, even with the thimbles, is something that lives in the digital world. I don't need the perception in the digital world because I don't have to touch any real object. In augmented reality, where I have both the digital world and the real world, I need a ring. So the ring is the right form factor for me for the augmented reality, because there I need the fingertip pulp in order to touch the environment. Okay? So this was the first paper of a few years ago that has been featured also on Science magazine, where they claimed that we are the first to invent a device, the ring, that was able to do augmented reality in force, augmented reality in tactile perception. For example, here, we were using the ring, we were using the bared finger, you know, free fingertip, to feel the force of this object, while we were using the ring to feel the force of the virtual object on top of it. Look, here I am going to grasp the real object, and I am going to feel the weight of this object plus the weight of the virtual object by using those robots that were applying tangential stress on the ring. Okay, is it clear, the concept, guys?
Sir, I have a doubt. Is that the weight of the object that is being placed, will it have a limit of how much I can measure the weight through the haptic feedback?
So there are, what's your name? So I can ask,
Yeah, my name is Aditya Ramesh.
Okay, Hadiyama Ramesh. So thanks for your question. So there are two problems here. One is that I'm feeling the weight of the blue object, not at the fingertip, but a little bit far away, no? Here, at the ring. But this is something that the brain can manage. Okay? So, of course, I'm not feeling the weight on the leg. So it's still here. And my perception system adjusts the thing and imagine the weight on the base as realistic as possible. Then the other thing is that you asked me is also important, is that with the cutaneous stimulation by motors, we can perceive up to 250 grams, more or less, 200, 300 grams, no more. Otherwise, beyond that limit, our receptors saturate and we don't feel anything. No, it's like we reach a plateau. We saturate the receptors. And this is very crucial. This is very crucial because if the blue object weighs less than 300 grams, I can be as realistic as possible. Of course, if the blue object weighs 30 kilos, I mean, 5 kilos, then I'm missing probably something because I had to use the kinesthesia. Okay, good question. Good question.
Yes, I understand.
Okay, so we were doing many experiments. The performance with the ring and with the thimble is very similar in terms of performance, but people liked a lot to use the ring because they consider the ring much more wearable than the thimbles. And of course, as I told you, I consider the thimble the best companion of the Oculus for virtual reality, for pure virtual reality. I consider the ring shape device as the best form factor for HoloLens, holograms, I mean, for everything that is in augmented reality or mixed reality. Do you agree?
Yes, sir, I do agree with it.
Okay, okay, wonderful, wonderful. Well, if you look to this table is very interesting because it's showing the level of wearability. No, we started from this robot applying forces at your fingertip that is not wearable at all. Then we had the exoskeleton that is quite wearable, but not as wearable as we do. Then we had the thimble robot that is very wearable. And then we moved the thimble design from thimble to ring concept to have this wearability by reducing the number of motors. Also from here to here, we were having a reduction because here we have 2 motors and not 3 like here. So in this case, we have 2 motors only. So you can apply normal forces and tangential forces along the cable. You cannot apply forces in this direction because you don't have the motors, okay? So you cannot stretch the skin in this direction because you don't have any cable actuated doing it. So going from 3 motors to 2 motors, we have 1 motor reduction for the sake of wearability. So because of the extreme wearability we want to have, we were reducing the number of motors to get the interaction. So I can say that so there is a trade-off between realism of the interaction, 3 motors, and wearability, ring. Good. Let's go to the question that, of course, we have a design where the same form factor can be used both as a ring and as a thimble. Like in this case, right? Okay, now we were doing even video games augmented with ring. This is a famous video game by Microsoft that sells with the HoloLens. We were feeling tactilely the kind of interaction with the laser. The question that one of your colleagues asked me in chat is if the pressure stimulus was the only one that we were doing on the skin, or if we have more, right? For sure, there are motors that apply this lift, the motion of this platform. Then we are using right now not the voice coil, but the piezoelectric technology to do vibrations and also thermal module. Why? Because when you so here there is an important element that I would like to stress your attention to call your attention to, is that when you develop technology for humans, you have to study the humans. Otherwise, you develop technology without knowing the perception system. No, for example, the screen of maybe we have a question here. I will go to the question of the weight immediately. So they are very light, actually. In the last version, each let me just see, each thimble weighs only 30 grams, so nothing basically, less than a ring. Okay, and so by the way, the weight is something that really affects So your colleague is asking if the weight of the device affect the realism of the interaction. Yes, and this is the reason why we have to design it very light. Okay, so going to the study of the perception system. Also, one example is this one that I want to give you in the visual modality. And in the visual modality, we have, you know that you can regulate the frequency of the screen, no? The frequency of the screen can go, even of the movies, can be 60 hertz, 20 hertz, 100 hertz, okay? But why? Why not 1 kilohertz? Not 1 kilohertz because the refresh rate of the retina of our eye is more or less 20-25 hertz, okay? So we are able to perceive 25 image per second on our retina. Now, if you consider the theorem of Shannon that duplicates the frequency, this means that we can send signals from 50 hertz on. Maybe 70 hertz, 80 hertz is enough. If you go with 1 kilohertz with the visual display, you are overkilling because you are using something that is not useful at all, because the refresh rate of the retina is 25 hertz, 30 hertz. So you don't need to go to the gigahertz with the display or to the kilohertz. So knowing the way we work, so our perception system is crucial to develop the right technology, okay? And this is also another aspect that I really like when we design tactile interface, because indeed we are talking about robotics developing haptics interfaces, which means at the boundary between the digital world and the human. Now, going back to how the haptic system works. So the haptic system works in this way. So we have perception of here in this case, no? We feel the pressure at the skin here. We feel the texture of the cover, okay? And we feel even the temperature. Actually, we are not feeling the temperature at all. We are feeling the heat conductance. So this is cold, okay? So the temperature goes from my body to this glass very quickly because of the temperature gradient, okay? So we have sensors trying to understand the heat conductance of the material, I mean, the velocity by where the heat goes away from our body to the other body, okay? We have sensors, receptors, to perceive the vibrations. So if I touch the wall, I feel the vibration of the wall. If I touch the glass of this thing, is much less vibratory because of the smoothness of the material. And of course, we feel the pressure. Now, if you want to design device accordingly, you need to have integrated in the device motors that moves the plate against the finger for skin. So you need to have motors that stimulate the receptors accordingly, okay? So you need to deform the skin, you need to vibrate the skin with a piezoelectric in the new version, and you need to apply temperature gradient, okay? And we use the Peltier cell. I don't know if you are familiar with the Peltier cell, but the Peltier cell is crucial because, I mean, it's easy to make warmer things. You just have, you need a resistor and you just put the current in the resistor and you generate heat, okay? But if you want to make it cooler than your finger, you need another technology. You cannot use the resistor. And this is done by the Peltier, a guy from France who patented this technology. We are using this thermal module that is a Peltier module. This is a demo. I mean, let me show you the demo with the device technology. Here we have 3 contact points. Inside there is the skin indentation with a motor. Then we can use the temperature of the liquid. We can use with we can feel the bottom here. We can feel now the temperature of the liquid that is being heating by the heat source here, and then we can feel vibrations of the material. For example, in this case, there is a bar that we are removing with this other plate, the part. The bar is vibrating because of this rotation, and you feel vibration through the material, through the device. Now, so right now in this, WeArt is developing the device that is called Touch Diver, that whose weight is 30 grams per thimble and 100 grams in the central control unit here on the wrist. We can do virtual reality and augmented reality, and it's integrated with all the VR and AR software engines like Unity and Unreal Engine, and it's really a successful project. We are collaborating with Medtronic, that is a huge company, medical company in US. We are also collaborating with IKEA, the furniture company in Sweden, for many applications. And we are also working with content developers. Okay, this is a demo that we did in this case, for example, we were tracking the fingers by using the lip motion on the Oculus device. Okay, do you have a question? For example, one nice control problem is that so the temperature module has a dynamic. Okay, so it can change the temperature, but it depends on the how fast you want to change it. So you can for example, if I have a thimble, like I think I have a thimble here. If I have a thimble like this, right, and I want to go from a hot point to a cold point, from a hot to a cold point, I can go, but not very quickly, because it depends on the transient time of the device inside the thimble. So the dynamics of the stimulators, in some sense, influence the virtual reality. So you have to design the virtual reality accordingly to the limitation of your technological device. So WeArt is the name that stands for wearable robotics technologies, but also we are playing with the concept of art, because we consider science like art, and in general we are like, I mean, always to my students I say that a paper, or I mean a piece of demo, whatever, is like a painting, no? And we are the artist who is painting it. And so it's a form of art, no? Because we are creating something that does not exist. So art is a deep concept of creativity, where the basic concept is that white piece of paper, nothing exists, and your idea becomes something existing after you paint your paper, your scientific paper. So I have another question here. Actually, we are very fast. There is so here there is Anil Sharma who is asking what's the delay from the generation of the signal that you want to display on your body with the haptic device to the real application of the force. No, we are very quick. We are very quick. We have a Bluetooth connection, fast Bluetooth 4.0. So there is, I would say, no delay at all, at least not perceivable delay. Okay. Other thing is about if we do this over the internet. For example, if I'm now doing something here with the virtual reality that is implemented in Jabalpur, then there is a delay of the communication, and that's really matter. Another thing that Ma asked is very interesting is the simulation of the fluid. It is extremely difficult to simulate the fluid. Fluid is very, very difficult for two reasons. Thanks for the question. One is the temperature. And the other thing is that if I put my hand in the liquid, then I perceive that all the parts, so it's really different from touching my face, no? So if I touch my face, then this part is involved, right? Only the inner part of the hand is involved. If I put the hand in the water, all my hand is involved. Not only the inner part, but also the outer part of the body is involved in the experience. So it's really, complete experience. And this is really difficult. So even this part of my hand is involved in the tactile experience with the water. So it's difficult. It's difficult to implement. Other thing is to touch, like now, something like if I have imagine to have a liquid here because of the difference of temperature, then of course I can feel it more realistically because it's not putting the hand in the liquid, but just feeling at your hand tip. So thanks for the question, but liquid is something that is still unsolved. Also because remember that when you want to do modeling, VR, you need a physical model of the environment. Now, if you are touching a virtual bottle, we have a model of the virtual bottle, that's okay, because it's a rigid body, but the liquid, you need a realistic modeling of the liquid. That, like, for example, the clothes. If I touch the clothes, no, then you need a realistic model of the things, because then I'm touching here, but I want to see this deformation here. So even if I don't have maybe I can be realistic here in this point, but I want to be realistic visually also here, no? So it's deformable objects and liquid objects is a challenge, is still a very open question.
Sir, is it possible that we can apply this to video games as well? Like making the video games to...
You know why we did the company? We did the company because, the first thing that we did, we patented the idea. First thing.
I see. Okay.
As university. Then, so there is a policy. So there are the inventors, I'm the inventor, and we own together with the university the idea. So the university is owner 50-50 with the inventor. Then I started going with my students around, and I saw a huge interest from people doing video games, huge interest. We went to talk with Facebook, Facebook is the owner of Oculus, with Sony, with HTC, with Huawei. So all of the big players working in virtual reality. So I saw a lot of attention. there, and a lot of interest. And then when we decided to open the startup with huge funding by another company in Milano that put the money and the expertise of the product design. For example, even the design. So I am super interested in, I'm also a little bit interested in the design of design, the aspect. And I participated to some of the meeting in the design of the device. I think I will show you I think I have the video. Have a look to this video. It's just 1 minute video of the WeArt. So what I want to say that even the design of the device in terms of ergonomy, even the package is a very interesting element that we had the collaboration with to create it. So the startup, so what we keep inside our core team is what we call the haptic core, that is the technology inside this thimble to generate skin indentation, temperature, and vibration. And even the methods that, as I told you before, the methods is something that lasts over the years. Delays, concepts is something that is in the core team of myself and the two PhD of mine we started this adventure with. Okay, let's go to another part of the talk that is probably very interesting for communication. Okay, so of course we can communicate, like in this case, with the audio communication, video communication, and but we can also apply touch. For example, Adia, if you are the doctor and if I am the patient, you can ask me to touch the base of the neck to understand the lymph nodes, how they go. No? Okay. So then we use this technology. This is my finger, right? This is my finger that is touching the neck. Okay. And this is your finger where the robot is on. 3 motors and the plate and the cables, right? Look here. I can touch the base of my neck and you will feel exactly what I touch on the other part of the world, okay? So the doctors feels exactly the tactile interaction that is happening here. Are you with me?
Yes, sir. Yes.
And this is what I call digitalization of touch. This is what enriches our data set, not only visual, not only geometric, not only text, but also tactile interaction with the environment. No matter if it is medical, if it is commercial, if it is design product, whatever, we can digitalize the touch for an experience of remote touch, remote in space, but also in time. I can, for example, interact with my daughter, okay, here on the left. I can record all the tactile, I can audio, video, tactile record all the experience, and then can perceive it after 10 years. And she can perceive what my hands were feeling where she was born. Right now, she's 11 years old. And she's also, at that time I was recording the interaction, and now she's able to feel the tactile interaction at my hand at that time. We can use this technology to impact, to help solve the isolation problem in the coronavirus social distancing issues, where people were at the hospital, at the emergency room. They were completely isolated. They were not able to touch any one of their family guys. So in this case, we can have tactile experience, so where the subject in the hospital can audio, video interact with the sister, with the son, whoever, daughter, whoever, and she or he can feel at their fingertip what she's touching. For example, let's, Aditya, do the simulation. You are my whoever, parent, family member, right? I'm at the hospital, okay? I want to interact with you. I want to feel a sort of handshake. You have the ring technology. You just touch yourself like this, and you show me. And I can feel at my finger this sensation with you, with yourself. You transmit on me. It's a sort of handshake, remoted, mediated by your body. So I became your hand, touching yourself and feeling on my side. It's clear, the concept?
Yes, sir.
Okay. So this is a sort of tactile interaction that will help to solve the social distancing issue. Skin, it's called the skin. It has a name. It has a name. There is a name for it. I don't remember exactly. Is the skin. So the name of skin deprivation in, if I write touch deprivation coronavirus skin, is called touch hunger. Touch hunger. So it means that I'm hungry of touch. Is a new form of suffering under corona. Okay, the missing of the tactile interaction is called touch hunger, and is a serious illness that we can partially mitigate with the use of our technology. Okay, good. Are you interested in this?
Yes, sir, completely.
Do you have questions in the audience?
Sir, I have a question, a query that can we differentiate different textures from this device?
Sure. We can go from any kind of material. For example, we have, I'm not sure if I can, thanks for the question. Helps me also to take some time from my voice. I want to show you something, if I can. This was a talk that I gave to Facebook. There was a big, I know, not a big, sorry, restricted meeting for the future of metaverse in the future of tactile sensing in metaverse, and I was presenting. No, it's not here. It's not here, by the way. So it's I can take you by words. So we have another device that we developed. It's a sort of mouse. You put the end on the mouse, okay? At the fingertip, there are the technology that I was showing before. You move this mouse on the same surface, and in the screen you can show wood, marble, ABS, metal, whatever material you want, okay? So the piezoelectric material has a bandwidth, has a frequency range that is large enough to simulate the interaction with any kind of material. Okay, thanks for the question. Now going back to this, we applied this technology also to surgery. We have been directly founded by Intuitive Surgical, the company that does the surgical robot, and we can take advantage of the tactile interaction. There is the robot that goes inside the body, and I think that you are familiar with it, no? And the surgeon manipulates from outside the robot, okay? Then this technology has no tactile feedback. So if you touch a stiff organ or a soft organ, you don't feel any difference at your hands, but only by vision you can recognize something. And this is crucial because, for example, if you want to operate the tumor at the lump, no? Pulmone, lump, that you break, no? The lump. If there is a tumor inside, you want to operate with the robotic surgery, with robot. Then the robot enters into the lump. In the lump there is air, the air, no, the oxygen. So when you make a hole, this air goes out, no, and the lump collapses because there is no air, and you don't recognize anymore by vision where the tumor is. You had the image, but you had the image with the lump full of air and oxygen, okay? If you make a hole with robot, with this robotic tool, then the oxygen goes out, the air goes out, and the lump collapses, and you don't know where the tumor is. So only if you touch, you can recognize it, okay? And you can do the surgery, right? Is it clear, this case?
Sir, is it not possible to penetrate the lung without making it collapsing? Without making it collapse?
It can, but not at this stage. So it can happen many times that the lump collapses during the surgery because you have to cut, you have to operate. You use the knife basically there to remove the part. So it's easy to create some issue. Okay. So in this case, we made. Sorry, let me go directly to the example. This is the real console of the robot. This is the real robot. This is just a sensor, and this is a simulated organ where there is a rigid surgeon does not know where the rigid bar is, okay? So the surgeon had to evaluate only by touch where the rigid bar is. So this was simulating the tumor, no? This was our add-on. This was our technology. The plate with the voice coil at that time, and the 3 motors, the 3 cables moving the plate accordingly. Okay, look to the experience. You see how this part deforms according to the sensor measurement. So it's stopping the video? Why? Sorry, it's going very slowly. Let me just remove the screen. You see here, according to the measurement, you have the skin deformation. Okay, so this is another application of remote tactile technology for medical application. Of course, this can be the real palpation during the televisit. It's exactly the same thing that happened on the finger of the surgeon. Okay. There is another part of the, do you have a question? No?
Sir, is it possible that we can integrate augmented reality and as well as haptic feedback into biomedical applications such as these? Because I think that directly looking from like from a far away point of view, far ground point of view, and rather than looking at it in a digital form, I think digital would give much more data than how we can perceive through our own eyes, if I'm not wrong.
So I think, I mean, for sure it will be possible. And I personally, this is actually my personal opinion. I don't want to, so this is just a feeling that I have. And also, it's my personal opinion, but I think that it can be easily shared with you. So I think, so I like more augmented reality than virtual reality, because I don't like to live a world, a life out of my physical environment, okay? I don't want to live, for certain thing, I am not a video game player. I had experience, but I'm not doing video games in virtual reality, apart from the knowledge that I need to have. I frequent them as scientist, not as a player, because I don't like to be just in a virtual world. On the other hand, I think that the future, so there is the digital world and the physical and real world. We need to take advantage of the digital world in any case. But living another life in the digital world, no. I personally don't like too much. So I like a domain where the digital world is a layer on the physical world. That is augmented reality, no?
Yes,
now,
yes.
Augmented reality is much, unless you have the glasses to show. For example, I'm talking with you and I see in the glasses your CV or I don't know, some text information or some picture. That's easy. Probably the easiest way to use augmented reality here in the near future. But it's different if I want to have 3 students in presence and 1 student here that is from remote, no? That's the real augmented reality I want to have. I want to have a shared class with 10 students here in Italy, 10 students here in Jalapalapur. I'm pronouncing well the name of the city.
It's actually called Jabalpur.
Jabalpur. So
Yes.
there are 20 students there, 10 here. I want to have 30 students together. So here there will be 10 students physically present and 20 students in augmented reality, and the other way around there, okay? That's the real augmented reality they want. So you can have a partial physical life with the students here and the remote experience with the augmented reality and vice versa, right? It's much more difficult because we have to mix. You think about the reference frame, frames, data. If you are in a virtual world, that's okay. You have the reference frame, it's one, you have to, the avatar is there, everything is there. But here we need to match the physical reference frame in my room and the virtual reference frame with the physical reference frame in Jabalpur. Okay, so it's really a matter of mixing data, much more complex than VR. So we are pushing a lot in VR because it's easier than augmented reality. Okay, and then another side is that in virtual reality, I admit to have a closed box to do everything here. In augmented reality, no. I want to have transparent glasses. I want to have holograms. I want to have transparent technology, much more difficult than an LCD in a box, 2 LCD in a box, okay? So augmented reality for me is the future where we need to go. It's more difficult and needs to have a technological push in virtual reality, and then we are ready to go in augmented reality. So I expect that video games will be the major killer applications for this kind of technologies in the near future, while the real jump will be in augmented reality, where even my mom will use it, not only my son.
Yes, yes,
okay?
Yes. I would also like to share a point that, in my opinion, I see the difference between the digital world and the physical world is the difference in data. That's what keeps the gap between the physical and the digital world. We do not have enough memory power to store whatever data that is existing in the physical world into a system. So achieving that would be one of the most, I think, how do I put this, is one of the biggest revolutions that would occur in technology. That is, we are able to replicate the physical world within a system. That means that we need to have whatever data that exists. Like, for example, if we have a leaf, and if we need to understand how the leaf grows within time, and we know that a tree takes a very long time to from becoming a plant to a tree. So that study of time, the time series, forecasting it, and also at the same time perceiving the present data together creates what we say is the digital world. And minimizing the gap requires the same amount of data that we perceive through ourselves from our own organs. So I mean, minimizing the gap, I think, would solve the situation that we are facing right now in communicating through the digital world. Like, for example, how do I put this as in simple words, is that how I'm trying to share my thoughts with you takes time in understanding. Yes, and same goes for others as well. So this process of understanding is happening in real time. As I am speaking, the process is being done. So to minimize the gap that what I am understanding as well as what others are understanding and what I am speaking, everything to happen in synchronization with along with the real digital world is what is missing in the present generation or the present ongoing research. So that is one thing I think that we should work on towards increasing or minimizing the gap between the digital and physical world. If I'm not wrong, I'm sorry, I just wanted to share it.
Another application that I want to mention that for the quality of life is that, for example, if I have a paretic hand, okay, then maybe I have something strange that I will show you in a moment. Then maybe when I interact with you and you are here with some HoloLens, you can see my real body, plus you can see an augmented digital hand that complete my body like if it was intact, okay? Or
yes,
maybe this is for health, but even for I mean, I'm not a fan at all because I think that the age should not be hidden, but even for aesthetic surgery, okay, we can have, I mean, you can talk with me and I can look like 30 years younger because of the augmented reality, because you have the helmet that makes me younger for some reason, no? So we can really have the power of doing a lot of things in augmented reality. That is exactly most of the things where people are spending money in now. So very interesting fields.
Yes,
okay.
Totally agreed, sir.
I want to open the other part of the lecture now.
Yes.
And yes, give me just a few minutes to make the switch of the slide. Can we take other so it's 22, sorry, can we take like 8 minutes break and
Yes,
we
please.
see for the last hour?
Yeah, sure. You can take a small break. No issues.
Hey, see you in 8
So
minutes,
we still
right?
have around, say, 4:53, 5:30. So we have around 37 minutes, Professor. So you can take a small break and come back. Definitely.
Sorry, how many minutes we have at the end of the lecture?
So it's around 37 minutes are still left. You can take
37?
a small break.
Oh, wait a second. 37 minutes.
Yes,
So
Professor.
there were 2 breaks and you have taken, I think, you can take a small rest.
I'm sorry. I thought it was more. I thought I had already still 1 hour, but it's 30 minutes, right? So no
Yes.
break. No break at all.
Okay, no issues.
Because I don't have time to show what I want to show you. So I will take, sorry, let's take a rest at the end of the.
Sure.
At the end of the talk. Okay, I'm sharing again the screen. I mean, still here. Sure. So I would like to take the opportunity to talk with you about, do you remember that we were discussing about tactile and, I mean, I'm sorry to skip the break, but we already had a sort of, online discussion with your students and students and colleagues, so we can keep going for the rest of the half an hour. So do you remember that we were talking about technology for touch and technology for manipulation? Now let me just introduce for the rest of half an hour the technology of manipulation, okay, for the quality of life improvement. Subject with a stroke. This subject was not able to, because of a stroke, is not able to have the right hand working as a paretic hand, right? He cannot do bimanual manipulation at all. Okay, He cannot, he cannot open the bottle. He cannot cut the bread. He cannot peel the fruit, the apple, for example. He cannot do all the things that we do with 2 hands. Okay. And going back to what I said before, the hand is so important that when you have a stroke, sort of fire in the brain, it's very likely that it affects the area of the hand, okay? Because of the many parameters that we need to control. So there is a large area. You know, at that time, I was looking to the literature in robotics, and I saw a lot of study for amputee. No, a lot of research for prosthesis. That was really cool, no? But you know, amputee is much less common than people with paretic limbs, no? We did some, I mean, you know, the number is much lower. I personally know many subjects with paretic hands because of stroke or other disease, but I personally don't know, I know, sorry, only 1 or 2 amputee that I met in the research area, not in my friends, families, or in my family, okay? I think that the same experience is for you. Even for me, I think that in, you know, when I will be 130 years old, it's more likely that I will have a stroke than I will be an amputee, no? And also because I think that as a human species, as humans, we need to solve the problem of amputee at the origin. We need to avoid wars. We need to avoid the bombs. We need to avoid all the things that unfortunately are happening all over the world, even close to us in Europe now. By the way, so what I want to do, instead of doing, I mean, you know what I meant, was what I was saying. Okay, so among the people that survive from a stroke, the 60% has impairments with the hands. So hand impairment is a huge problem. But you know, what we can do with this kind of people? You know, it's really difficult to think about what we can do. Can you see me? Okay. Hello?
Yes, we can see you.
Professor.
Okay, I was not seeing you anymore. So what happens is that we cannot. So I was surprised that there was no technology for people with paretic limbs, but only for amputee. But you know why? Because it's even if it's technological, very difficult how to connect the arm with the robot. You know, all these kind of things, the mechanics of the hand, very, very difficult issues. But from you know, from an anatomical point of view, it's almost easy. I don't have the hand because I'm an amputee. I simply put a robotic hand. I don't have the leg because of the amputee. I simply put a robotic leg. But for people with a paretic limb, it's really difficult because the hand is there, is anatomically present. I cannot remove it and put a prosthesis. So it's difficult from, you know, getting ideas to invent something that was able to help these guys, even if these guys had the hand there, present, perfectly present, okay? That was really a difficult task to invent something. So, of course, there are special tools, but we don't want to use special tools. There are particular exoskeleton that you can use in the rehabilitation facilities and things like that. but there was nothing as simple as something that I'm going to present now to you. So by looking to the end of my daughter, and also to get some strange ideas on the symmetry of the hand, so we said, okay, let's make it as simple as possible. So what you need to help these people doing a grasp? So help me. So answer me, what's the minimum number of fingers that you need to make a grasp? What's the minimum number of fingers that you need to make a grasp?
3.
3.
3, okay, but even 2, like this, no?
Yes.
3 is better. 2 is okay, no? 3 is much better, but the minimum is 2, right? Okay. Of course, to be honest, it can be only 1 if you use the palm, right? Because if you use the palm, you can use the thumb and the palm to do the grasp. So we said, okay, but why don't we use the palm, sorry, the residual hand of the human, sorry, the paretic hand as a palm, and we just add a thumb to the subject, okay, to make this happening. So we invented this extra finger, and this extra finger is the thumb that is able to make an hybrid grasp between the human and the robot. So this is the 6th finger, a supernumerary wearable finger that is helping people with impairment to do bimanual task. This is a soft version design of the finger.
Are you sharing your screen?
Professor, are you sharing the screen?
Let me.
You had not shared the screen, Professor.
Let me do it.
Yeah, now it is.
But before you were seeing it? No, never?
No.
Ah, okay. So sorry. I was just quickly going through the, because this is the guy who had the stroke, okay? And he cannot use the right hand anymore. Okay? So this is the prosthesis research that I was talking about. No one was done for people with paretic limbs, okay? We can use something like an exoskeleton, but not as simple as the idea of this is the end of my daughter, where I was talking about the minimum number of fingers to grasp an object. And this is what I was showing now, the extra finger.
Yes, close.
Okay. Still give me 1 second more, because I think that for some reason this presentation is not going as good as I was thinking to. Give me only 1 minute. Okay. Let me just go to another set of slides because I think that they will go smoothly. Okay, here we go. Let me just stop sharing this. Let me close PowerPoint that is eating a lot of things. Let me share now the screen again. Okay. Can you see it? Can you see it?
Yes, it is visible, sir.
So this is the paretic limb subject that was not able to do by manual manipulation anymore. This is, the prosthesis I was showing to you. This is the end of my daughter. This is the idea of the extra finger. Very simple. So one finger and the palm, realizing the grasp like this one. Okay, the thumb and the palm. Okay, and this is the realization of with the soft device. Okay, so this robot is a robot soft device, one motor that adapts to any shape of object because of the compliant design. The nice thing is that we were asked to design this device waterproof in order to let them do interesting things. So this is very useful because people with a paretic hand can use the extra finger to have compensation of the functions missing in the end, but they will have a reason to move the upper limb again. Because if you have a sort of gripper at the end, you start moving the arm again. And one of the people, all the people experts in rehabilitation knows and say that moving the part of the body is the first rehabilitation aid for people with this kind of impairments, no? To avoid that the muscles goes down, basically. So look to the kind of force that this finger can express. He's peeling the apple. So we are quite obsessed by the concept of wearability. This finger becomes wearable and goes under the jacket and becomes a finger only when it is needed. And this is really motivational for the subject. This is the design of the finger, soft. How we interface it. This is cool, in my opinion. So we interface this. I will explain you with this example. We have a ring. This is a subject who has a stroke. This is a subject who has a stroke and cannot move the hand, and he cannot perceive anything in terms of tactile perception because we had the impairment in motion of the hand and motion of the skin. Can you follow me? Okay. Now, when in the case of grasping this glass, okay, when the robot here, this white part, the robot closes, like in this video, he has no idea of the force that the robot is doing against the arm. Okay, he has no idea at all, right? So there is no idea on the force. So the subject does not know when he has to lift the arm, okay? Because he does not know if it's pushing or not, okay? Then we are using the haptic feedback on the other side of the body, on the healthy part of the body, to provide a signal that says to the human, look, there is enough force here, you can lift it. So the haptic feedback here, the motors here that we were explaining in the first part of the lecture, is providing a stimulus that tells the subject, go, lift. So it's like he's perceiving the extra finger. He's perceiving the robotic finger. And here there is a button that switch that starts the motion. So the human is under control, has the full control of the robot. Look, it starts switch, the finger moves, squeezes. When there is enough force, the system vibrates here and he knows that he can lift it. Okay? So this is what I call sensory motor augmentation. So there is an action that is recognized by the interface, like the switch that activate the actuation of the robot, that has a sensors, that provides measurements, that through the haptic feedback provides the perception on the other part of the body of the human. Okay, so there is a full integration between a robot and the sensory motor interface. I call this sensory motor interface, recognizing the voluntary action that activate the robot, that is perceived by the human thanks to the haptic feedback. Have a look to the system again. Human activated switch is recognized by the robot, activate the motor. There is a sensor that perceives the force and provide the feedback to the human that senses the robot and complete the action. So a full integration between the robot and the sensory motor system. We are testing many other activation like EMG and other system we can talk about. This is a subject that has been using our device just 5 minutes after I met him. Was immediate the way he was using it. And now he's able also to close to put the cap on the bottle. He was never able to do it. It was a complete success for him, just with a single finger more, the additional thumb. Look. And this is really motivational for them. Okay? Look now, this is unfortunately is in Italian, but there are the captions in English. This is the subject who is the owner of this sailing boat. He was not able to control the boat anymore after the stroke. Look with the finger. 1 minute.
Io sono Alessandro Bondi, ho 52 anni e ho avuto 4 anni fa un ictus. Ho sofferto per molto tempo, poi ho visto un barlume di speranza nella tecnologia che mi ha portato a sperare di tornare sulla barca a vela. Mi sono avvicinato all'equipe di Domenico Pratichizzo, che è l'ingegnere che ha inventato il sesto dito.
Nel caso di Alessandro è estremamente utile perché creerà una presa di tipo ibrido, una presa fatta dall'uomo e dal robot. Consiste in 3 parti principali, un motore che attraverso dei tendini trasmette il movimento a questa parte rigida e flessibile che consente di afferrare degli oggetti adattandosi a qualunque forma.
Mi rende in qualche modo un cyborg.
I hope you got the idea. Very, very, emotionally engaging. And what I have to say is that something happened in this research, even also because we became a friend with this patient. That is our pilot studies expert. So, and when you engage emotionally with someone you are doing research with, the communication is much more fluent and things goes very nicely. Okay, let me then I will take all the questions at the end. Okay, so then can you see me?
Yes, sir.
Okay, then also this became a patent, and the patent became a company. The company is called Venovia. It's not it's an early stage with respect to WeArt. We still don't have the product on the market. Will be probably next year. It will cost more or less like an high-end mobile phone. And it's look at the very nice design. This is I was at Las Vegas at the Consumer Electronics Show showing this device in 2020. Now there is also the voice control. We are putting a lot of attention on the wearability to let people with only one hand to be able to wear easily. the device. And these are all the publications. I mean, I'm going to the end, and because I want to take some questions from you. This is my last paper on nature, machine intelligence, on human body augmentations. That I'm really proud of this paper because got accepted there. He took the cover of the Nature journal plus the editorial. So the editorial of the editor-in-chief is on our paper and on the concept of human body augmentation through the robots. These are all the patents I was talking about, and I made from these patents 2 real companies that are called WeArt and Existo that I co-founded actually, and I am the visionary guy of I'm giving the vision, the directions. I am not involved day by day in the company, of course. And this is a book that I wrote with one of my PhD student coming from Pakistan and now professor in Abu Dhabi.
Professor, your screen is not shared.
Oh, sorry. I don't know why. Sometimes we miss this screen aspect. Let me do it again. Did you see the boat?
Now we are able to see. Yeah.
But what is the last thing that you saw?
We could see your this.
The boat.
Yeah, this was visible. This we had seen.
This is the company.
No, this we.
Okay, so this is the company I was talking about that came from the patent. Okay, and this is the interface, the wearability. I was here in Las Vegas showing a consumer electronics show, showing the device. We put a lot of attention in the wearability. For example, I was showing how easy to wear this device with one hand only, thanks to magnets, for example. Okay, and these are all the publications of this extra finger stuff. I'm particularly proud of the Nature machine intelligence paper that I published a few months ago that got the cover of the journal, of the issue of the journal, and also the editorial of the editor-in-chief that the editor-in-chief wrote is on our paper. These are the patents I was talking about, and 2 of them generated the companies. I'm involved as a visionary scientist that gives the vision. I am not involved in the day-by-day operations. And this is a book that I wrote. I'm quite proud of Irfan Hussain. Irfan Hussain comes from Pakistan, and he did his master in Pakistan. Then he went to work, I think, in a company in Korea for an engineering company. Then we met, and he came to my lab, and he became really productive. He changed completely his life because his life was in the industry area in Korea. He was not really attracted by that kind of life, and now he's a leading scientist in the field. He's professor in Abu Dhabi, and basically we wrote together this book on augmentation that was the major subject of his PhD, and in some way is close to your educational system because it's close to your area. We are now extending this concept to third arm, perfectly integrated with the body of the human. We recently got a 4.6 million project from Europe. I have the honor to coordinate on human augmentation through sensory motor interfaces for people with upper limbs disabilities. So I want to thank you for your attention, and I am open in the last 10 minutes to the question you want to ask to me. And I hope you enjoyed. For me, it was really a pleasure to give this talk.
I really enjoyed your lectures, sir. Thank you so much.
Thank you.
Yes, sir, it was really great, sir. Having to interact with you, like, sir, I'm working on haptic feedback for upper limb prosthesis. So is it possible to stimulate the residual limb in a continuous mode of vibration and not discrete?
Yes, let me, okay. So the most interesting technology we are dealing with for this is this one. So if you use one cable that squeezes a part of the body with one motor only, the squeezing can be really continuous. It can give you the idea of the prosthesis grasping something. I suggest to use this kind of technology. Maybe I can send you some paper you can get inspired to create your device. Vibrations are useful, but you can change the intensity, but I think that this is another option you can really consider to provide continuous information and not discrete ones.
Yes, sir. Okay, sir. It will be really grateful. So if you could send some papers that could motivate you.
Can you, if you send me an email, then
Yes,
it's easier. I can answer.
Okay, I'll send you an email, sir. Thank you, sir.
Thank you. Some other question?
Hello, sir. I have been following your papers for my PhD thesis. I am working on prosthetic hand design for my PhD thesis. Sir, I had one doubt. Sir, how does supernumeral fingers compete with hand designs based on, suppose, human postural synergies for reduced actuators? Suppose reduced actuator designs.
Okay, I'm not sure I got the point. I'm trying to repeat. So thanks for following me in research, and you are mainly talking about the work that I did on synergistic control of human hand, of robotic hand, right?
Yes, sir. Means suppose supernumeral fingers, how does that compete with the hand designs that are based on postural hand synergies?
Okay, so the postural hand synergies for a robotic hand is a way to control the robotic hand, okay? So to model the robotic hand. So I can have a hand that is fully actuated and I can control it by using some postural synergies like this, like a primitive, no? Or I can have hands designed just with one motor to have the motion that is the postural one. And this is one story.
Yes. Yes.
The other thing is the finger. The finger is, in some sense, is postural based because it's, you know, it's only, you can still see my screen, right?
Yes, sir.
So this is one motor, right? And
yes,
this is one, I don't know if I can have some nice, oh, this is cool. Okay, let me unshare this. Sorry, unhide this, unskip this. And let me just show this. So we design, the finger is only one motor with the cable, but we can decide the way the finger closes by designing the compliance of the joint. Okay, so yes. This element, this black element, as a young module that we can design and we can simulate. So by changing the design of this is the same finger with a different compliant module, we can change the way the finger closes, right?
Yes.
Okay. So this finger closes differently from this because this finger has different compliant nodes from this one. So we changed this black element, okay? So this is a synergy that we decide by changing the K. So, and we are controlling the finger. We are controlling the finger by using this, this was showing the robustness of this. So in some sense, we are using the synergy approach even for the finger, and we are studying the synergies in this case. Of course, are not synergies inspired by humans, but are synergies that should be inspired by the function. So we want to grasp. So the action of doing something inspires the synergistic control of the finger and provides the right compliance for the design. I hope that I answered your questions.
So, sir, means the supernumeral finger design is a different approach of human augmentation.
So human augmentation is a big concept that goes beyond the extra finger. For example, in my view, we can augment our body not only with wearable robots, but also with grounded robots. So I can feel a grounded robots as an extension of my body thanks to my interfaces. Okay, so I'm thinking to the augmentation as a general concept that goes beyond the wearability. But then you say, but you said that the wearability is important. Yes, it's very important. But in this case, we are taking, in this case, the robot is grounded, but the interface is wearable. The interface is in the cap and is full of haptic feedback. So the wearability is for the informative part. So the interface should be wearable, but I can, and I call it sensory motor interface, and I can control any robot. In my project, there is a part that I will be able to control domotics, so actuated doors with this kind of interfaces. I hope I answered your question, or at least I inspired your research.
Yes, sir. Yes, sure.
Some other question? We have 3 minutes. Can I have the comments from my colleagues, Professor Aparagia and the coordinator of GIAN, or the people that were more involved in this project that involved me, if I can have your comments about today.
Yes, thank you, Professor Domenico. It was very nice. We learned a number of things today. And we will be having more lectures from you. So more detailing of the things, basically, you will be discussing, I hope, in the next few months. Thank you very much.
I hope I made these lectures, these keynotes interactive, because I think that when we use this remote technology, we should be really try to find, I was also moving my body because I don't like to stay seated on the chair, to engage more the attention of people. So I think that from remote, we need to put a lot of attention in try to talk with the audience in some sense.
Yeah, interaction is more needed actually. It is
a lot.
Then it becomes more interesting also.
Couldn't agree more, sir.
Okay. So a special thank to all you students, colleagues, scientists that stayed with me, and a special thank to Professor Aparagia and the coordinator of GIAN and the other colleagues that motivated me to apply for this great project that you have in India. Hopefully, we will cooperate in the future on single projects, and let's see you for the lectures from tomorrow. The lectures will be mainly done by me, but of course there will be my team, my assistants that will help me in some specific parts. You will see more faces, also to have more engaging lecture, as I do in my classes. Okay?
Sir, I have a question regarding your lectures, that would there be any practical sessions that we may be or practical inspirations that we may be able to try during the lectures?
Will be a little bit difficult to do this with real robots, but luckily enough, we have. We will probably use MATLAB. I don't know if you have MATLAB.
Yeah, we do have access to MATLAB.
If you have access to MATLAB, we have some toolbox. For example, there is a toolbox that I developed with my team. It's called, I will show you. It's called The Art of Manipulation. It's an online course that I will so I need to share the screen again. Is it still sharing?
No, no.
Okay, so this is a course that have been founded directly by MATLAB. It's more on robotic grasping, and as you can see, the course is called The Art of Grasping, because for me, robotics, science in general, is an art. Of course, you can find the video lectures that we will refer to, but there is also a toolbox that is this SynGrasp that we will be using in at least in one lecture. Okay?
Yes, I understand. Would there be a lecture in this GIAN course demonstrating this SynGrasp?
Sorry, one more thing is that, of course, I will show robot running from the lab and technology running from the lab. What is difficult is to have the robot, the device running on the other side. We will see in details the extra fingers and the interfaces with the cameras. But hands-on will be on software.
Got it, sir. So there will be hands-on.
Yeah. So thank you, Aditya. In fact, we have another session at 5:35. I hope you know that. So thank you so very much, Professor, for such a wonderful session. And we, as you very rightly say, we expect more participation from the participants. Please feel free in asking questions, interacting with the professor, so that we can make it more meaningful.
Okay. I'm asking one thing. Can you please send me the picture?
Yes, Professor. We are going to send you the picture and YouTube link also. That
Vijay, have a screenshot at this moment also.
Screenshot. Okay.
Yeah.
So let's have a screenshot. We request you to please unshare your screen so that we can have a screenshot.
And participant, kindly start your video.
Did you do
Yeah,
this?
please start your video. Yeah.
Okay, we already did, no?
Every session they say GIAN people.
Yeah, but you can send me that. That one is fine. We don't need to do another one. That one is fine. If you can send it to me via email, is perfect, or whatever you want.
Vijay, is it necessary that you do it for every session? I think so.
Yeah, it is necessary.
So today, in fact, one is fine, I think. One is fine.
Okay.
Because he did not have any break in the session, so one is
fine. One is fine. One is fine. I want that one. Okay. Please. Thank you.
Thank you. Thank you all.
Tomorrow. Bye-bye.
Thank you, Professor. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So thank you all the participants. We are meeting tomorrow at the same time. So please join just before time so that we can start on time. We are meeting tomorrow. Have a great evening, all of you. Enjoy your dinner with your family and friends. Yeah. Thank you. Bye.
Thank you.